To summarize the various steps that we looked at, you consider the function during the design first in terms of the nature of the loading and the equations that describe that. Then you specify the constraints, whether it's stiffness specified, or whether it's geometry specified, or whether it could be a failure load, or it could how strong the material should be, or kind of fatigue properties, for instance, or fracture toughness properties. Objectives then involve either minimizing mass, minimizing cost, minimizing environmental impact, maximizing energy storage. These are all some things that we'll look at eventually. In this class, we'll look at some variations of the first two. And for instance, in the previous case, when you're looking at minimizing mass, you looked at dealing with minimizing this function or maximizing the reciprocal. So the generalized derivation is as follows. You want a performance metric P of a structural element. It depends upon the functional requirements of the design, the geometric parameters of the design, and the material properties of the design. This can be represented generically in this manner. If we separate those three variables and just simply consider as a product of three different functions, one that's entirely determined by the function, another that's entirely determined by the geometry attribute, and the third that's uniquely represented by the material properties alone, we can look at how to be able to select materials in this particular case by just focusing on this aspect for the index. And then the performance can be maximized when we maximize this index over here. So the tie rod, we had seen that we wanted to minimize the mass that can carry this load F. And so if you minimize the mass, you want to minimize the cross-sectional area if length is fixed. But if you reduce it too much, it will exceed the overall failure strength. And we said, okay, this is a product of the three functions, F times L times rho over sigma F. Alternatively, you could rearrange this term and get a specific mass or a density reduction based on working with these parameters. We had also looked at this type of a product of three different equations, one describing the function, another describing the geometry, and the third describing the material index. For a stiff beam, we had this type of a parameter for the stiffness, and by taking into account the moment of inertia, we wanted to deal with reducing the mass in this case, and we decided that this was a product of these three terms. If you rearrange this slightly, you will have a constant over here, and then this term over here, and then the material index term. So during a translational step, which is the focus of this class, here is a summary of different aspects of the design process. We define the overall design requirements by these four steps in terms of the function, the constraints, the objective, and the free variable. You list the constraints, you develop an equation for the objective, you identify the free variables, and you substitute the free variables from the constraint equation. So you basically populate the space over here based on answering these questions. And you try to group the variables into functional requirements F, geometry attributes or parameters G, and material properties M. And you want to either maximize or minimize the performance metric. Then you read off the material index and express a quantity M that optimizes the performance metric P. So one way to look at this material index is as a criterion of excellence. How to get from materials that are good enough to materials that are best for the job. Here are some common examples for various geometries, various optimization criteria, and various constraints. Function, objective, and constraints. They not only cover physical properties such as rho, but mechanical properties such as E or sigma Y, cost attributes, thermal properties, electrical properties. From a structural perspective, the first six parameters are the most commonly used, where you want to either minimize weight or you want to be able to minimize cost. Okay. This table over here shows the interrelationship between minimizing mass or minimizing cost as an objective function. It is summarized for three different kinds of geometries: tension for a tie rod, bending for a beam, and bending for a panel. These are three very common design situations. And based on a stiffness limited design or a strength limited design, you have this set of 6 material indices. In the first column is stiffness limited. It depends upon the modulus and the density. If it's strength limited, it depends upon the yield strength and the density. These indices change quite a bit. That's for minimizing mass. If you are instead minimizing cost, then in the denominator, you introduce this material cost per kilogram term. We looked at quite a bit of this particular term over here. Make sure that you are able to derive in a similar manner each of these different possibilities. And remember this one for a strength limited design for a bending beam as well, because it comes up quite frequently. You are introduced to EduPack and you have downloaded the software by now. So let's take an example of this material index, e to the power half by over rho for a light stiff beam. If you rearrange these terms and square both sides, you will get e square equals to rho square times m square. And if you take logs on both sides, you will have log e equals to 2 times log rho plus 2 times log m. So in an E versus rho plot, this slope of 2 will allow you to identify all light stiff beams, and then depending upon the value of m, you will be able to move it up and down, right? Depending upon increasing this value m, and decide which one is the group of materials that you would select and which ones you will eliminate based on these considerations of the function. In the case of the beam, for instance, what we have just seen is the slope is 2, and then you move things around depending upon the value of m that you want and choose it off the intercept.